Welcome back to the fourth section of chapter 4. This section starts the second part of the chapter. The first part we were looking at how to work with matrices, what they are, how to add, subtract, multiply, things like that. The second part of the chapter we're going to look at a couple more properties of matrices. Like today we're going to be looking at the determinant, see how it can be used. But each of these sections we're going to see how we can use a matrix to solve a system of equations. That's what we did in the last chapter. And so Cramer's Rule is one of the ways that we can solve a system of equations using a matrix. So let's look at our learning targets. First one, I can find the determinants of 2x2 and 3x3 matrices. And I can use Cramer's Rule to solve a system of linear equations. So the first thing is the determinant of a 2x2 matrix. Well, what is a determinant? A determinant is just a measure of a matrix. It's a number that we get that describes the matrix and can be used in some actually fairly surprising ways. To find the determinant of a 2x2 matrix, we're going to take a matrix, just the general, A equals A, B, C, D, and we're going to take the main diagonal. Oh, before that, the determinant, the notation for the determinant is using the straight up and down bars. So this would be a determinant of A, or we could just write this. This is the determinant of the matrix that's inside of it. Now it's the straight up and down ones instead of the square ones. Now what do these look like? Yes, they look like absolute value bars. What do you think the most common mistake is when someone is asked to find the determinant? Yeah, they just make everything positive because they think it's absolute value bars because they weren't paying attention. The straight bars is the determinant. And to find it, we're going to take this main diagonal, A times D, and we're going to subtract the other diagonal, B times C. And that gives us it's just a number. It's not a matrix. The determinant is a number. And so it's just A times D minus B times C. So let's see it in action. Here we find the determinant of this 2x2 matrix. And so we're going to go 7 times 2 minus 5 times 9. 7 times 2 is 14. 5 times 9 is 45. So we have 14 minus 45, which is negative 31. That would be the determinant of this 2x2 matrix. They're not too tough to find. That's why I say the biggest mistake is people seeing it and thinking it just means absolute value and not finding the determinant. And so, try a couple. I have two of them for you to try. We have the determinant of 1.5, 0.25, 6, and 2.5, and the determinant of negative 3, 40, negative 5, 6 and 2/3. Alright, so try these. Again, it's just a couple little multiplications and a subtraction. If it didn't have decimal points and fractions, you'd probably be done by now. But go ahead, pause this, and then come back in a minute when you have found the determinants. You think you have them? Alright, you probably do. So this one, we're going to take 1.5 times 2.5 minus 6 times 0.25. 1.5 times 2.5 was 3.75. 6 times 0.25 is 1.5. Subtract, and we get 2.25. Pretty easy? Yeah, oh, it has decimals. Ooh. This one has fraction. Ooh. We do the same thing. Negative 3 times 66 and 2/3. It's negative 200. Negative 5 times 40. It's negative 200. So we have negative 200 minus negative 200. Minus negative means plus, so this gives us 0. Can we have a determinant that equals 0? Of course we can. 0 is just a number. But for whatever reason, people get freaked out when they get an answer that equals 0. It's just a number. Now, some interesting stuff happens when the determinant is 0 when we're solving, but it is a legitimate determinant. And so we're going to use these determinants to solve systems of equations using Cramer's Rule. And so what Cramer's Rule says is if we have a system of equations, this is just a 2 system with 2 variables, we can look at these guys. Notice I have x plus y equals a number, and x plus y equals a number. That's very important because we're going to take these numbers and put them into a matrix. The only thing that tells us what these numbers are is their placement. So the placement's very important. So we have x plus y equals a number, x plus y equals a number. We're going to take these and we're going to make a coefficient matrix. It's the matrix of the coefficients. It's literally A, B, D, E. And we're going to find the determinant of that. And we're going to call it D. So D is the determinant of just this A, B, D, E matrix. Now, we're just going to find the determinant of 2 more matrices and then do a little bit of division. The ones we're going to find for x, we're going to take the same determinant, only we're going to replace the x column, the A and the D, with the C and the F. So we'll have CF BE, and we're finding the determinant, and then divide by D, whatever this number is. And for y, we do the same thing, except instead of replacing the x column, we'll replace the y column with the CF. And then we divide by D. And so let's see what this looks like. So we have a system of equations. The first thing we need to do is we need to put it in the right order. So we're going to add the y over to get 6x plus y equals 2. Subtract the 2y to get 3x minus 2y. And then subtract the 1 so it equals negative 1. Now it's in the right order. We can find our determinant. D is going to be the determinant of the coefficient matrix. So the determinant of 6, 1, 3, negative 2, which we can find. 6 times negative 2 is negative 12. 3 times 1 is 3. So negative 12 minus 3 is negative 15. So D is negative 15. That's what's going to go in the denominators of both of these. Now for x, we're going to switch out the 6 and the 3 for a 2 and a negative 1 and find the determinant. And then divide by negative 15. And for y, we're going to switch out the 1 and negative 2 and put in the 2 and negative 1 and find the determinant. And then divide by negative 15. So we do this. 2 times negative 2 is negative 4. And then negative 1. So negative 4 minus negative 1 is negative 3 over 15. And here we have negative 6 minus 6, which will be negative 12 over 15. And then when we reduce, negative 3 over negative 15 is just 0.2. And negative 12 over negative 15 is 0.8. And so that's how we can use Cramer's Rule. Now, could we have solved this just using systems of equations like what we did last chapter? We could have. And there's always people that will say, well, then I guess I don't need Cramer's Rule. I'll just use what we did last chapter, and I won't learn the new stuff. Well, first of all, that's a horrible thought process. But second of all, I can give you questions where you can't solve it the normal way. How would I do that? Instead of giving you a system of equations, I'd give you this determinant with the A, B, D, E, no numbers, equals negative 15. This determinant with the C, B, F, E equals a number, like say negative 3. And this determinant equals a number, like negative 12. And then all you'd have to do is know what to divide. You just have to say, oh, hey, the coefficients are there. I just divide this one by this one. And I just divide this one by this one. And it's really easy, but you need to know what you're doing. So practice Cramer's Rule, Don't just do it the way we did it last chapter. That's not going to work out for you in the end. And so, there is one more thing with Cramer's rule. As we're looking at these equations, what could happen that could make this go awry? Remember the last slide, I said that, hey, the determinant can equal 0. Funny stuff happens when it does, but it can. Well, if this equals 0, all of a sudden we're dividing by 0. That's no good. What then? Those just give us our special cases. Remember, we're solving systems of equations, and we have a couple different things that can happen, specifically with the number of solutions. In the normal case, where we get one solution at intersection, D just doesn't equal 0. Like here it equaled -15. We got a point. So if D doesn't equal 0, there's one solution. However, if D equals 0, that's when we get the other two. If D equals 0 and at least one of the numerator determinants equals 0, then there's infinite solutions. And so that would be the same line. And if D equals 0 and no numerator equals 0, then there are no solutions. And that's where there would be parallel. So let's take a look at something like that. Here we have a matrix. It's already in the proper form. So we can find D. D will be the coefficient matrix, 4, 1, 8, 2. We can multiply. 4 times 2 is 8. Minus 8 times 1 is 8. 8 minus 8 is 0. That shouldn't be surprising because I just told you that we're going to do one like this. So D equals 0. So we just need to find the other two matrices, or the other two determinants, and see if they equal 0. Now, if we find one and it equals 0, we don't need to find the other one because we only need at least one of them. So, the first one, we're going to replace the 4 and the 8 with the -6 and the 9. We can multiply. -6 times 2 is -12. Minus 9 is -21. More importantly, it's not 0. And we can replace the 1 and the 2 with the -6 and the 9. So 4 times 9 is 36. Minus 8 times -6 is -48. 36 minus -48 is not 0. It's 84 for those of you keeping score at home, but it is not 0. Being that neither of these two are 0, so no numerator equals 0, there are no solutions. And so that would be the special cases of Cramer's rule. Most of the time, it'll end up like this. You get a number, and that's great. But every once in a while, you get something where the determinant equals 0. So, moving on, that was all with 2 by 2 matrices. We can also look at the determinant of a 3 by 3 matrix. I know when I learned this, I took a few years of classes on matrices. It's called linear algebra. But when I learned it, we were taught an equation for 3 by 3s that was long and obnoxious and had interchanging positives and negatives, and it was really confusing to try and remember. And there's another one for 4 by 4s, another one for 5 by 5s, and it was horrible. Instead of that, I had figured out another way of doing it, which when I looked in the book, it turns out that's the way the book shows it too, which is fantastic. I love when they do things smart like that. Where this isn't going to be an equation, it's going to be a process, and it's going to be very similar to the 2 by 2s. And so, what we're going to do, and this also expands to 4 by 4s very, very nicely. So what we're going to do is we're going to take our 3 by 3 matrix, and we are going to extend the matrix by 2 columns, and we're just going to repeat the first 2 columns. Why would we do that? It's because we're going to be multiplying diagonals, and that gives us some diagonals to multiply by. And so now well, let's multiply by the diagonals. We're going to have the first one is 2 times negative 2 times negative 3, plus the next diagonal, negative 1 times negative 4 times 0, plus the next diagonal, 0 times 3 times 1. And so those are all the diagonals there. It's 3 diagonals. We have a 3 by 3. Technically on a 2 by 2, we could do the same thing, but the 2 middle ones actually just cancel each other out, so it doesn't matter. So we have 3 diagonals. And then we're going to subtract. We're going to go the other way. We're going to take that diagonal, 0 times negative 2 times 0, plus 2 times negative 4 times 1, plus negative 3 times negative 1. And we're going to put all those together. So we're going to add all these up, and we're going to add all these up, and we're going to subtract them. And that'll get us the number, because the determinant is a number. So when we multiply these, 2 times negative 2 is negative 4, times negative 3 is 12. Negative 1 times negative 4 times 0, 0. 0 times 3 times 1, 0. Over here, 0 times negative 2 times 0 is 0. 1 times negative 4 times 2 is negative 8. And negative 3 times negative 1 is 9. And so adding these 3 up, this is a tough one. 12 plus 0 is just 12. Minus, add these 3. 0 plus negative 8 plus 9 is 1. So 12 minus 1 is 11. So is it kind of long and obnoxious? Sure. But all we're doing is multiplying and then adding or subtracting. So how about try one? We have the matrix 1, 2, negative 1, 4, 0, 1, 1, negative 2, 3. Try this. Extend it by 2. Do the multiplication. I would show some steps because there are a lot of places where you can make mistakes here. And then pause the video and come back when you're done. All right, welcome back. How do you think you did? Well, let's see. First, we'll extend. So it's just the first 2 rows again. And then we can start multiplying our diagonals. 1 times 0 times 3. And then plus 2 times 1 times 1. Plus negative 1 times 4 times negative 2. All right, that gets us the first one. Then minus. We're going to have to go 1 times 0 times negative 1. Negative 2 times 1 times 1. And 3 times 4 times 2. That's the second one. And now we can multiply. 1 times 0 times 3 is just 0. 2 times 1 times 1 is 2. Negative 1 times 4 times negative 2 is 8. Over here, 1 times 0 times negative 1 is 0. Negative 2 times 1 times 1 is negative 2. And 3 times 4 times 2 is 24. We can add. 0 plus 2 plus 8 is 10. Minus 0 plus negative 2 plus 24 is 22. And 10 minus 22 is negative 12. How'd you do on that one? Lots of places to make little mistakes, but thankfully when you have a 0 or 2 in there, it simplifies it quite a bit. And so we can use this to solve 3 by 3 systems of equations as well. The process is exactly the same with 3 by 3s as with 2 by 2s. If we have our matrix, we're first going to find the coefficient matrix, which would be this one, and find its determinant. So D will equal the determinant of these, which is negative 9. If you're following along at home, you can do that. Check your work. And then for our variables, we're going to do the exact same thing that we did with the 2 by 2s. To find the x1, we're going to replace the x column with the answer column. Find the determinant, divide by this one, negative 9. For the y's, we'll replace the y column. Find the determinant, and then divide by this determinant. And for the z's, we'll replace the z column. Find the determinant, then divide by this one. So x, we replace the x column. We find the determinant of this new matrix, divide by negative 9, because we know this one's negative 9. For the y's, replace the y column, find the determinant, divide by -9. And for the z's, replace the z column, find the determinant, and divide by -9. I will leave this one up to you if you want to do it. It's great practice finding the determinants. And when you do, you should get x equals 1, y equals 3, and z equals 1. But I have faith in you. I think you can find the determinants of these. And so, with that, I will see you next time. And until then, happy mathing.